Optimal transport is a topic with a long history, perhaps starting with Monge in France and then really flowering with Kantarovich in Russia and many other. It's led to 2 Fields medals, great connections to probability theory, PDE, and geometry. And so I'm delighted we have an expert on this topic here who just joined us, Krzysztof. Please.
Thank you very much for your kind invitation and for introducing the topic and myself. So I'll be speaking about optimal transport martingales and how they can be used to partition space and what are the applications to optics in geometry. So let me first give a very general overview. So how can we solve a mathematical problem? Well, we can look at some easier problems, and then perhaps it may happen that our problem can be partitioned into the simpler blocks. We can solve the simple blocks and then glue the solution together. So there are many examples of how this can be, in many different fields, how this can be done. So in linear algebra, we have Jordan blocks and diagonalization, and in functional analysis, spectral decomposition. In algebraic geometry, we have irreducible components. So the algebraic sets that cannot be written as a union of 2 proper algebraic subsets. In representation theory, we have irreducible representations. So if our representation is semi-simple, then it can be written as a direct sum of irreducible representations. In probability theory also, if we consider a Markov chain, then if it's called irreducible if the probability between any 2 states, the transition probability is positive. In algebra, we also have simple groups and prime ideals. And I'm sure that you would be able to name many more examples. So I will focus now on one particular way to partition our problem into some simpler problems. And this can be obtained through some variational principle. So suppose we have 2 sets. So I will start with a very, very basic problem. Suppose we have 2 sets on a plane, finite sets, both of them consisting of n points, and altogether in general position, meaning that no 3 of these points lie on a common line. So we would like now to match every point of x to a single point of y in such a way that the line segments that will originate from this matching are pairwise disjoint. So here we see random 10 red points and random green points. So red points are x, green points are y, and we would like to match red points to green points in such a way that these segments are disjoint. So a priori, it's not immediately clear that such matching exists, but now I will convince it does, and the solution is very simple. So there is a finite number n factorial matchings, and we look for the one that minimizes the sum of the lengths of these intervals. And this matching will do the job. Why? Because for the optimal matching, if we had an intersection of 2 segments, then we would be able to find another matching which would have a strictly better the sum of the lengths. Namely, instead of this matching, we would replace the matching with that one, and by the triangle inequality, that would be strictly better. So the problem that we have just seen was actually to find an optimal transport map from the set x to the set y with the measures on x and y uniform. So what's the optimal transport problem? So suppose we have 2 probability measures, mu and nu. Nu lies on the set x and nu lies on the set y. And we are interested in finding a map f from x to y such that the push forward of f of nu with respect to f is equal to y. So what does this condition mean? So here we have a nice picture. So here we have the space y with measure nu. Here we have a space x with measure nu. So the condition that f push forward mu is equal to nu means that whenever we take any set here in y, and we look at its per image, then the measure mu of A is equal to the measure mu of F inverse A. All right, so in other words, the mass that we have transported by F to A is the same as the mass in the per image. So among such maps, we are looking for the one that minimizes this integral. So C here is some given cost function, and we are interested in minimizing the average cost. So this problem was first studied by Gaspard Monge in his paper Mémoire sur la théorie de Blas et de Remblas. So de Blas means excavations and Remblas means embankments. So we are transporting some sand, for example, from these excavations to these embankments. And we are interested in, he was interested in how to do it in the most optimal way. And the cost function that he considered was a distance function. All right, so it was, for a long time, it was not known whether such optimal map exists for let's say, for absolutely continuous measures on manifolds. But even more is true. It's true that if we consider arbitrary measures, then it might happen that there is no transport map that pushes forward one measure onto the other. Why? If you consider mu to be a Dirac delta measure concentrated on a point, and nu to be a sum of two Dirac delta measures, then clearly there is no map that pushes forward this delta measure to the sum of two delta measures. And this problem exactly is solved by a relaxation that Leonid Kantorovich in 1942 proposed as a solution to this problem. So he suggested that we should study instead of looking for a map, we should look for an optimal coupling between two measures. So an optimal coupling is a probability measure on a product of x and y, such that its marginals are equal to mu and nu respectively. So the marginals are the push forward by the projection maps onto respective coordinates. So now in this example where we have this one delta measure and two Dirac delta measures here, clearly an optimal coupling exists. So the optimal coupling allows us to consider probabilistic. So a mass at one point can be split into a mass in two other points. So this was a contribution of Kantorovich, and another contribution of his was that he showed that the optimal value of the optimal transport problem is equal, thanks to certain convex duality, to the supremum of integrals of functions u with respect to the difference of the two measures, and the supremum is taken over all one Lipschitz functions from our space, metric space X to the real line.
The second thing he didn't do by himself.
This was with Rubinstein, but for his contributions to optimal transport theory, he was awarded the Nobel Prize in economics in 1976, if I remember correctly. So the contribution of Kantorovich the contribution of Kantorovich and Rubinstein of identifying the supremum as the dual problem was used by Sudakov in 1979 to propose a solution to the problem, which unfortunately turned out to be wrong. It was spotted by Ambrosio that there is a flaw in his argument, but still it was a substantial contribution. So Sadakov showed that any optimal transport is constrained by sets which are pairwise disjoint and are called transport rays. This is correct. This is correct. This is correct. I will explain what was not correct in what he showed. The transport rays are the set of maximal slope of the optimal one Lipschitz function here. And they have this property that they are pairwise disjoint, so they partition our space. And moreover, the transport has to occur along this transport race. So what Sudakov didn't notice is that if you disintegrate an absolutely continuous measure with respect to this transport trace or with respect to arbitrary partition, it may happen that the conditional measures are not absolutely continuous, or it could be even so that they are atomic. And in that case, his solution would not work, but then it was remedied firstly it was remedied by Caffarelli, Feldman, and McCann. So their paper was published in 2002, and the paper of Trudinger and Wong was published in 2001, and Ambrosio in 2001. But as I was told by McCann, is that their paper was first. So actually, the first complete solution, therefore, was presented by Evans and Gangbo in 1997. They used completely different methods, yet they still used this notion of transport trace, but their methods were relying very much on partial differential equations and so-called p-harmonic maps. So then they considered these p-harmonic maps, took p to infinity, and they found out a solution through consideration of infinity harmonic functions. Okay. So let me stress it again that here this transport trace form a partition. So this relates this optimal transport problem to this first slide of my talk. So what's the gain that we have this partitioning? The gain is that the transport trace are constrained by this transport trace, and therefore the mass of mu and nu on each of the transport trace is the same. And there is one more property that is preserved by this transport trace. And this is the property of the curvature dimension. So here I need to explain what's the curvature dimension property. So if you have a manifold, or more generally metric measure space, then it enjoys this curvature dimension property. Intuitively speaking, if the Ricci curvature of this space is bounded from below by kappa, and the dimension of the space is bounded from above by capital N. So this curvature dimension property in the metric measure spaces was introduced by Lott, Sture, and Villani, and in that setting of metric measure spaces, so metric measure spaces are simply spaces which are metric and equipped with some measure. And in that setting, the curvature dimension properties are simply requiring that the entropy functional is convex along the geodesics with respect to the Wasserstein distance. So the Wasserstein distance is again the distance on the space of measures defined by optimal transport. So there's another instance of optimal transport that occurs here. So it turns out that optimal transport is not only useful to what I will be speaking about in a moment, but also it's very useful in studying the curvature properties of the space. So Klartak in 2014 showed that if we disintegrate the measure on such space that satisfies the CD condition, then the conditional measures on this transport trace, and the transport trace are one-dimensional, will also satisfy this curvature dimension properties with the same parameters. And then Cavalletti and Mondino extended the Klartak result in 2015 to the setting of metric measure spaces. So Klartak proved it only in the setting of weighted Riemannian manifolds. So this is the theorem of Cavalletti and Mondino. So suppose we have a metric measure space XDM. So D is metric, M is a measure, and it satisfies the CD condition. And suppose we have a function F. Then, using the methods of optimal transport, we can show that there exists a partition of X into geodesics. So this geodesics will be the transport race that I have been just speaking about, such that the measure M can be disintegrated with respect to this partition. It means, on a very intuitive level, it means that the Ricci curvature is bounded from below by kappa, and the dimension is bounded from above by n. So, but it also involves the curvature of the measure. So, for example, if we are on a flat space, on a Euclidean space, and we set n to be equal to infinity and kappa equal to 0, then this condition means exactly that we are dealing with log concave measure. If n is finite, then we are dealing with a measure with density which is 1 over n concave. And in the curved space, this condition also involves Ricci curvature. So we have this integration, and this measures mt, which are concentrated on the transport trace. They are concentrated on the disjoint transport trace, right? And this integration has also this property that this transport trace satisfies CD condition, and also our function f integrates to 0 with respect to m. So how this theorem is proven is it's proven by taking an optimal transport from normalized measure f plus dm to f minus dm. And so we take this optimal transport, we get the transport trace, we disintegrate, and that's basically it. So why is this theorem interesting? Tau is, so we have our space, we have partitioning. On the entire space, we have measure m, and we can look at so tau is so theta, right?
So this is an element of the partition?
Tau is element of partition, and yes, and theta is the push forward of the partition map of our original measure with respect to the partition map. So theta is a measure on the space of transport trace.
This triple is a notation for an element of the partition.
All right, so how can we use this theorem? One of the applications is the Levy-Gromov isoperimetric inequality in the setting of metric measure spaces, which wasn't known before their contributions. So what's the isoperimetric inequality? So let us suppose that kappa is non-negative, and we have some space that satisfies the curvature dimension condition, and we have some set A in this space X. So let us now take, and we are interested in this isoperimetric ratio. So the isoperimetric ratio here, we look at the surface area of the set A, and we divide it by the measure on the space. Yes. Yes, I'm just about to explain. So, and having this space with CD Kn condition, we look at a sphere in the model space. So model space is exactly the sphere, so curvature is positive. We look at the sphere of this constant curvature and dimension n, and the spherical cap is just a spherical cap on the sphere. So we look at the spherical cap of the same measure as A, and then the Levy-Gromov isoperimetric inequality tells us that this surface area of the spherical cap is a lower bound for the surface area of our set A. And that's it. But there is more gain to the methods of Cavallenti and Mondino, and this is that the methods allow us also to obtain rigidity results. So we can ask ourselves what happens if we have some space X that satisfies this CD condition and some set A for which we have equality here. So it turns out that in that case, our space itself has to be a spherical suspension of some space. So a spherical suspension is basically you take your space X as an equator and then you glue a sphere around it. And also they also were able to prove that if there is a bounded discrepancy between these two quantities, then there exists some space to which our original space is close to. There is some spherical suspension to which our space is close to. All right, so the question that I am most interested in is how can we extend these techniques to several constraints. So up to now, we have been considering just one constraint, namely that the integral of f with respect to m is equal to 0. And now we are interested in how we can extend it to several constraints. So let us suppose we have some probability measure mu on space x, and we have k functions, f1 up to fk, that integrate to 0 against this measure mu. X is some space. Well, it could be a manifold, it could be a metric measure space, but we can assume that's a manifold. Yeah, I've written here submanifolds. If these are submanifolds, then we should ask X to be a manifold. That's correct. So now we are interested in whether we can partition our space X into at most k-dimensional submanifolds, for which the functions will again integrate to 0 against the conditional measures of our original measure. So in case X is Euclidean space, this is known to be the case, and this is due to the people named Cannon, Lovash, and Simonovich. This is the so-called localization technique. But it is not known whether such partition can be obtained in curved spaces. So what would be the perspective applications of this, of such generalization? They would include multi-bubble problem, which I'm going to speak about in a minute, estimates for higher order eigenvalues of Laplacian. So the one-dimensional localization allows to bound the Poincaré constant for our measure. So Poincaré constant is a bound for the first eigenvalue of Laplacian. So using this, I hope to obtain some bounds for higher order eigenvalues of Laplacian. And also there is famous conjecture of Cannon, Lovash, and Simonovich, which basically tells that if you have a convex set and we look at so-called Cheeger constant, then this Cheeger constant, which is basically isoperimetric constant, can be bounded by a universal constant independent of dimension times the Cheeger constant, but only calculated for half spaces. So what's the multi-bubble problem? So the multi-bubble problem is, in a way, generalization of the isoperimetric problem. So if you look at the isoperimetric problem on a probability space, then you are given some volume V, and then the complement has volume 1 minus V. So they sum up to 1. And then you are looking at the set with minimal surface area. But the surface area coincides with the surface area of the interface. So a generalization is that if we look at some number of volumes, V1 up to Vk, then we would like to find a partition of our space. If we have a probability space, then we would like to partition our space into these sets of these volumes in such a way that the surface area of the interface is minimal. So this is a picture. So it's known that the energy of the soap bubbles is proportional to the area, and therefore the soap bubbles should answer our question how such multi-bubbles, optimal bubbles look like. So one possible approach to this generalization to several constraints was proposed by Clartak in his paper of 2014, but this was turned out to be wrong. All right, so there is so to approach this problem, perhaps one should first start with the very basic problem that I have started at the beginning and look at its generalizations. And these generalizations were considered by Noga Alon. So he proposed in 1990 the following problem. So suppose we have n sets in Rn, all finite and of the same cardinality. And as we assume that they are altogether in general position, so that no n+1 points lie on a codimension 1 subspace. So this is what the situation looks like in the three-dimensional space. So we have 10 red points, 10 green points, and 10 blue points. And we would like to find, so in the two-dimensional case, we had segments. And now we are looking for n-1 dimensional simplexes. So we would like to find this k simplexes such that each simplex has precisely one vertex in each of the xi's. So here we are looking for triangles, and we would like each triangle to have one vertex red, one vertex blue, and one vertex green. And we also want these triangles to be pairwise disjoint. So it was proven by Noga-Alon and Akiyama in 1989 that such simplexes exist, but it's not known whether there exists an efficient algorithm. So the method of Akiyama and Alon, it uses Borsuk-Ulam theorem, and actually the proof is quite simple. And it is known that such Borsuk-Ulam cuts are at least exponentially expensive. So there is no way we can compute this in a reasonable time. So here is the Borsuk-Ulam cut of our configuration. So the Borsuk-Ulam cuts are done consecutively. If we partitioned ours, so we cut our problem into two. Each of the problems will consist of half of the points of the original number. And then we inductively continue until we arrive at convex cells, each containing exactly one red, blue, and green point. And these points are then joined together by a triangle. And these triangles are then disjoint because the cells were disjoint. All right, so let me now speak about another approach to obtaining partitions, which also is related to transport, but this time it will be martingale transports. So we have two probability measures on our end that are distribution of a one-step martingale. So let me remind you what's a martingale. So a martingale is a pair x0, it's a pair of random variables, x0 and x1, such that the conditional expectation of x1 with respect to x0 is equal to x0. And then one can look at the all couplings pi, which are distributions of such one-step martingales. And we can look for pi which is minimizing some cost function, some expectation of cost function. So where does this problem stem from? It stems from mathematical finance, actually, when it is used to find what was the appropriate pricing of options without any a priori assumptions on the model. So it was done in 2013 in R1, and later, I think in 2015, in high dimensions. So one of the most interesting results in this theory is that there exists a partitioning of the space into so-called irreducible components, but these irreducible components are convex sets, and they have not only the property that any martingale transport is constrained by this set, but also within this set, we can move mass by such martingale transport from wherever to wherever we want. So this is another candidate that would be useful for obtaining such partitions. But we can, so the problem here is that these sets can be of arbitrary dimensions. So there is no dimension reduction that we were interested in. So perhaps we can obtain some dimension reduction using a different version of the previous problem. So now let us take A to be a linear subspace of functions on some space X. And let us assume that you have two measures mu and nu, which are distributions of one-step A martingale. And by A martingale, I mean such pair of random variables x1 and x0, such that the conditional expectation of A of x1 with respect to x0 is equal to A of x0. And this is supposed to be happen for all functions in our linear space. So if A is the linear space of linear function, then we exactly get the martingale condition. So I have shown that this in this setting, we also have a partitioning of the space into sets, which also enjoy these properties that we can move mass freely within the sets. But this time, the sets are not convex, but they are aconvex. And aconvex is defined in a completely analogous way to how we can define holomorphic convexity. So now let me finish the talk by asking, can we find a suitable family A such that all the elements of such partition are lower dimensional? Okay, so that's all what I had to say. Thank you for your attention.
Any questions?
So you had the problem where you partition the space into k-dimensional. You ask for a partition into k-dimensional submanifolds. Can these submanifolds be interpreted as like the transport rays for some transport problem?
Well, yes, I have some idea how this can be done, but they are not yet complete.
I have one question. So you mentioned the Borsuk-Ulam, the approach to the theorem of Nogalon and co-author. That you said that is exponential, but that's not. Maybe you can elaborate on that because it's not known to be exponential, right? It's fixedly hard.
It's not known to be exponential. Well, as far as I'm not an expert on this topic, but I've seen some papers that were claiming that we have a box of size, I think, n times n, and we have n points inside, and to make such cut, one needs at least c to the power n. That would cost at least c to the power n. But yeah, I don't know. I'm not an expert on this topic, but maybe if you would have something to add to this, I would be grateful.
So there is a class of problems related to Nash equilibrium, Borsuk-Ulam, fixed P completeness, and also it's a class of sets that are believed to be exponential. I believe they're not proved to be exponential, but maybe there is some finer subset inside for which it is proved. This would be interesting to track down. Any other questions? Okay, if not, let's thank Krzysztof for a wonderful introduction.